Hi class, welcome to exercise 7a, exploring parabolas. In today's lesson, our examples and pre-learning will be example 1, identify key features of parabolas. And for this example, your pre-learning will be questions 1 in the new book and questions 3 in the old book. And then we'll work on example 2, transforming parabolas. And for this example, your pre-learning will be questions 2, 3 and 4 in the new book and questions 4 and 5 in the old book. So welcome to the new block of learning in this unit. Quadratics will be involved later on in this block. But today's lesson is all about the key properties of their graphs. Alright, let's move on to the introduction. Just like linear equations make lines, quadratic equations make parabolas. So let's explore them. And seeing I'm drawing parallels with linear graphs, let's recall what a linear graph is. And hopefully you remember that I like to start thinking about a graph with a table. So here's a table I prepared a little earlier. So here we have the rule y is equal to 2x minus 1. So for each value of x, there's a rule that dictates what the related value of y will be. So for example, when x is equal to minus 3, y will have to equal 2 times minus 3 minus 1, which is minus 7. And doing the same thing when x is minus 2, minus 1, 0, 1, 2 and 3, we can see that x will be minus 5, minus 3, minus 1, 1, 3 and 5. And we know that each column will become a point on the line in Cartesian coordinates. So for example, this point here where x is minus 3 and y is 7 becomes this point down here. So obviously this point is in line with the minus 3 in the x direction and minus 7 in the y direction. And we make it look like a point. And let me mark in the rest of the points that you can see I've already put there. And let's draw the line that connects them all. Let's not forget to mark in the y-intercept. Now of course I said the line that connects them all, but another way you could express that is that this is the line that they're all on. And for any other value of x, its value of y would match up with a position on that line as well. Now we wouldn't have to calculate all these points because there are key features that tell us everything about a graph. And for a linear graph, it is the gradient and its intercepts. In the linear relations unit, we also found out that we could work out anything we wanted to about this line just from 2 points. And so just like we know that a linear equation or rule becomes a line, a quadratic equation will become a parabola. So let's start with the most fundamental quadratic, y equals x squared. So minus 2 squared is 4, minus 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So if I was to plot these on a set of coordinates, and let me mark in those axes, and just like in the linear graphs, each one of those columns is a point, so let me quickly mark those in. And the shape that fits them all in is this one, which is what we call a parabola. But before we delve into the properties of a parabola too much, let's have a look at this GeoGebra applet. And hopefully you're going to see how these quadratic equations make parabolas and start to see some of the properties yourself. So while I'm using this applet, I'm going to demonstrate the equations that are actually in the textbook. So first we'll look at y equals x squared. So you can see here when x is equal to minus 3, x squared is 9. If I move this slider, we can see all the whole number values of x from minus 3 to 3 and the corresponding values of x squared. And notice as I did that, each one of them corresponded to a new dot. So this dot up on the top left here is x equals minus 3 and y is equal to 9. And we've got x equals minus 2 and y is equal to 4, etc, etc. Now this smooth line is the line that represents any number x squared. Now this is what we call parabola. Now let's look at minus x squared. So this is just all the points of x squared, but the y values are negative. And we can see the parabola that fits these points. And this parabola here is nothing but the original parabola reflected in the x-axis, which is not surprising when we think about turning numbers into their negative values. Now, let's have a look at x minus 2 squared. So our first value here is minus 3 minus 2 squared, which is just minus 5 squared, which is 25. And let's have a look at the other values of x. And so our last one, for example, 3 minus 2 squared is just 1 squared, and that is 1. And let's have a look at the parabola that fits these points. You can see that it's still the same parabola, it's just been translated to the right. So take note that minusing inside the brackets moves us to the right or the positive direction. Now I've got one final parabola for you to look at, and that is x squared minus 3. So here's our first point here, and you can see how its y value is 6. And that's because minus 3 squared is 9, take away 3 is 6. So let's move out that slider and have a look at all the values of x between minus 3 and 3 and fit the parabola to these points. And once again, you can see we've got the original parabola basically just slided down or translated down 3 places. Okay, let's go back to OneNote and take some notes about these key properties. So that little applet will be a good reminder to you that no matter what graph you've got, it's just an infinite series of points. So if you ever want to use it anytime, you know where the link is, it's here in the OneNote. Alright, so just like linear graphs have key properties that tell you everything about them, there are some key properties of a parabola. And these properties tell you everything you need to know about a parabola. So let's draw some coordinates with a parabola. Now a key point in a parabola is what's called a turning point. This turning point locates the center and the height of the parabola. So I've marked it in, but let me actually note it. Hopefully you can see that's totally fundamental. That is where the parabola is centered. So if we have a quadratic equation of y equals x minus h squared plus k, our turning point will be a minimum. And of course that means it's the lowest possible point in our parabola. And you can see that's the case in this one. But if you have a minus sign, such as y equals minus x minus h squared plus k, then you'll see that sort of parabola that's reflected in the x-axis. And in that case, our turning point will be a maximum. Another key feature is what's called the axis of symmetry. And let me mark that in here. My sideways writing is even worse than my normal writing. All right, so one distinguishable point about the axis of symmetry is that it's a vertical line that passes through the turning point. Also, you should be able to see that the parabola is completely symmetrical around the axis of symmetry. Another key feature is its x-intercepts. And just like every other graph, it just means this is where our rule is equal to 0. So for the x-intercepts in a parabola, we're saying it's where the quadratic is equal to 0. And as you know from our work with quadratics, that means there could possibly be 0, 1, or 2 x-intercepts. And finally, we've got the y-intercept. And this is just the value of y when x is equal to 0. And that means there's always only going to be one y-intercept. Just to make another point about the axis of symmetry that's going to become very important later on in this block, what we mean by symmetrical is that any points that have the same y value will be the same distance from it. So here we've got two x-intercepts. Their distance from the axis of symmetry will both be the same. Let's just call that d. And if I was to pick out another point that was the same height as the y-intercept, then their 2 points would be the same distance from the axis of symmetry, and let's call that e. So this is a very handy feature that's going to help us find a lot of other things about a parabola. So far you've been introduced to the turning point, the x-intercepts, the y-intercepts, and the axis of symmetry, but there's one other property, and that's called dilation. Now we didn't demonstrate that in the last applet, so let's assume that if I could draw that this parabola here is y equals x squared. Then if we have some value of a that's greater than 1, then the parabola y equals a times x, y equals a times x squared, this parabola will be thinner than the original parabola. If I had this other number b that was between 0 and 1, and I created this parabola y equals b times x, bx squared, I don't know why I keep making that mistake. Anyhow, this parabola will be wider than the original parabola. Now don't forget to take note of these points, but let's use GeoGebra to look at these properties a little better. It should help make up for my lack of artistic skills. Okay, I've built this applet so that you can see the equation change more fluidly, just by using these sliders. Also notice that I've got the equation for parabola in green. So first notice that the parabola gets thinner as I increase the dilation and wider as I reduce it. Hopefully you're taking notice of the equation changing as well. And let me just move that dilation factor back to 1. So let me zoom in so you can see the value of this equation at 1. Now notice that the y value is the same when x equals -1 and x equals 1. Notice if I change the dilation factor, that y equals the dilation factor at -1 and 1. So here we have 2 and y is equal to 2 at -1 and 1. And if I made that dilation factor a half, we'd see the same thing with y equal to half at -1 and at 1. Let's zoom out again and translate this parabola horizontally. Notice how the axis of symmetry changes. That's this dashed line here you can see. I've also got the equation for the axis of symmetry there, and notice that we say that x is equal to 2.2. That's exactly how you describe a vertical line. Also notice that the value in the turning point down here is the same value. So you can see the 2.2 is the x value in the turning point and x equals 2.2 up there. Now we're going to delve into that a little bit more in further lessons. Now if I leave this parabola translated horizontally, but also start to translate it vertically, the x and y intercepts, which I've made blue, become a lot more apparent. And the turning point, you can see, still has the same x value as the equation for the axis of symmetry. Now in this lesson, the aim is that you'll be able to distinguish a parabola just with the turning point, intercepts, and or the dilation factor. And one other thing we'd like to look at is reflecting a parabola in the x-axis. Notice that the x-intercepts haven't changed, and the y-intercept is the negative value of what was before it was reflected. Let me show you again. I'm not going to say a lot about how to figure out the dilation factor equation from the parabola in this lesson. However, you may wish to start trying to make connections between properties of a parabola and the quadratics we've been studying through the first half of this unit. That will be where we go with the parabolas in the next few lessons. So once again, you can always come back and use this applet yourself. The link is in the OneNote. All right, I'll see you in the next section. All right, so as we've covered in the introduction, the key features of a parabola are the turning point. So for two parabolas like this, the turning point is the point that is at the center of the graph. It will always be the maximum or the minimum y value. There's the axis of symmetry. So for two parabolas like this, the axis of symmetry is the vertical line that passes through the turning point. So let me mark that in. So for these turning points, which I'll call both of A, B, the axis of symmetry is just x equals the x value in there, so we'll get x equals a. And of course that means that the y value of the turning point is b, so let me mark that in one of these. And the important thing about the axis of symmetry is that the parabola is symmetrically reflected by the axis of symmetry. And finally, we have the x and y intercepts. And that's just where the parabola crosses the axes. So for this parabola here, so a is the y-intercept, and b and c are the x-intercepts. And of course, just like every other graph, x-intercepts are where y equals 0. It's also important to note with a parabola that there could be 0, 1, or 2 x-intercepts. And the y-intercept is where x equals 0. And there's always one y-intercept. Also note that intercepts can be written as numbers or coordinates, but the turning point is always a coordinate. Marking it on the axis means you don't necessarily have to state it's a coordinate. All right, let's have a look at example 1, where we're going to determine the key features on the following graphs. All right, in part A, we have this graph. All right, you can see how difficult it was to draw that. So in this case, the turning point is 1 and -4. And I had to correct that. Obviously, you can see that it couldn't be -1 because we're on the right side of the y-axis. Now, the next thing I'm going to look for is the axis of symmetry, because that's super easy, right? That is just x equals the x value of the turning point. So therefore, the axis of symmetry is x equals 1. So the x-intercepts are marked in already, and they're -1 and 3. And of course, I said you could write them as coordinates, so that would be -1, 0, and 3, 0. And finally, the y-intercept is -3, or 0, -3. That's depending if you want to write it as a coordinate. All right, let's move on to part B, where we have this parabola. Goodness me, that's getting bad. Hopefully you're still able to use the distinguishing features. Anyhow, we can see that the turning point is actually on the x-axis there, and therefore the turning point is -2 and 0. Okay, so an x value of -2 and a y value of 0. And therefore our axis of symmetry is the x equals -2. And there's only one x-intercept, that is -2. Or -2, 0 if you want coordinates. And the y-intercept is marked in at -4. Or 0, -4 if you want coordinates. Okay, so that's pretty straightforward. Just finding some things on the graphs, knowing which one is a turning point and which one is intercept, etc, etc. So just pause that video now and you can quickly get through questions 1 in the new book or questions 3 in the old book. And then we'll see you in the next section. Okay, here's a fun fact. There's only one parabola, technically. So why should you study it then? Well, that's because it can be stretched and squeezed with dilation. The number that multiplies x squares controls dilation. So for y equals a times x squared, if a is greater than 1, the parabola is thinner. If a is between 0 and 1, then the parabola is wider. The parabola can also be reflected in the x-axis. So if y is equal to some negative value a times x squared, then the parabola is upside down. And of course, upside down means reflected in the x-axis. The parabola can also be translated vertically and horizontally. So if y is equal to x minus h all squared, then it's translated horizontally, if h is not equal to 0. And if y is equal to x squared plus k, then it's translated vertically. Of course, k is not equal to 0. Of course, please note that a parabola can involve more than one translation. So for example, if y was equal to -2 times x minus 2 all squared plus 3, has quite a few transformations going on. So firstly, because it's got that minus sign there, we know that it's reflected in the x-axis. And the number 2 means it's going to be dilated positively. There is a value that's not 0 for h, so it's translated horizontally. And the plus 3 there, so it's also translated vertically. So it's got the lot. All right, let's get straight into example 2, where we're going to complete the table for the properties of the following graphs. And I hear you say, what tables? Well, here's something I prepared a little earlier. And that was inspired by the fact that, well, I can't draw. So these are part A, B, and C. And the red dashed line there is a typical parabola, and the blue one is the one that we're interested in. And I've written the equations here in the table. So for part A, y equals 4x squared. Does it have a maximum or minimum? Well, it's a positive one going up, so there is a lowest y value, therefore it's a minimum. Is it reflected in the x-axis, i.e. is it positive or negative? And the answer is no. What is the turning point? Well, it actually happens to be at 0, 0. Let me mark that in. What is the y value of x equals 1? Well, that's 4. And let me mark that in. And is it wider or narrower than y equals x squared? Well, it's definitely narrow. Okay, and that's because we've got an a value greater than 1, which is 4. All right, let's look at the next one, x plus 2 squared. So is it a maximum or minimum? Well, it's a minimum. Is it reflected in the x-axis? No, it's positive. What is the turning point? Well, let me mark that in. And there you can see the x value is -2 and the y value is 0. And when x equals 1, that's off the graph. So 1 plus 2 squared is 3 squared, so it has to equal 9. Is it wider or narrower? Well, there's no a value, there's nothing multiplying the eventual x squared, so it's actually the same. And finally, part C is y equals -x squared plus 3, which is the last one on the right here. It's a maximum, you can see, because it's a negative one. And that means it's definitely reflected in the x-axis, so that's a yes. Hopefully you can see the connection between minimum, no, and maximum, yes. All right, so the turning point is this point here. That has an x value of 0 and a y value of 3. And our y value when x equals 1 is, well, let me mark the point in. That there is definitely 2. But you could just do that mathematically in the formula. So minus 1 squared is minus 1, plus 3 is 2, which is the same. All right, so is it wider or narrower? We have a minus 1, which is like multiplying by 1 as far as a dilation factor goes, so it is the same. All right, so that's that table filled out. It's pretty straightforward, just like the last example. So how about you just skip straight on now and pause that video so you can do questions 2, 3, and 4 if you have the new book, or questions 4 or 5 if you have the old book. And hurry back so we can summarize this lesson. But make sure you do come back for the summary. So this lesson was all about the properties of parabolas. In the following lessons, we're going to be drawing connections between these parabolas and quadratics. So there is a point for us to do the parabolas and quadratics in the same unit. All right, so for this lesson, a successful student will know the shape and symmetry of a basic parabola, y equals x squared. Be able to identify the key features of a parabola from a graph, and be able to observe the impact of transformation of y equals x squared. All right, good luck studying all those features and transformations. It's really important that you understand these aspects of a parabola so we can connect them to quadratics in our next class. So I'll see you there, either on a video or in the classroom. Bye.